Today we are going to look at lesson 6-2. It's all about reciprocal functions. So the reciprocal function, this is our parent function, and everything that we've learned about parent functions still remains true. So we're going to take this parent function and we're going to move it right, left, up, down, stretch and shrink it, and reflect it. And so here you see all of those things happening. So if you recall all the other functions this year that we have graphed, if you do something inside the function, remember the function is 1 over x, so this is 1 over x. If you do something inside the function, it moves it right, left. And it's the opposite of what you think it is because it says a minus here in front of the h. If you do something outside the function, it moves it up, down. This a is what tells us whether it shrinks or stretches, because you can take this a and factor it out in front. And then if the a is a negative, then it will reflect. And so you're going to see all of that down here. So let's just go ahead and add all of that information for you here. So for a stretch, we would look at the absolute value of a, because remember, if a is negative, it means a reflection. It has nothing to do with a stretch or a shrink. So if the absolute value of a is greater than 1, that's going to be a stretch. If the absolute value of a is less than 1 but greater than 0, it's a greater than symbol, you're going to have a shrink. And then of course if a is less than 0, meaning it's negative, you're going to have a reflection across the x-axis. Why the x-axis? Because if a is negative, it's really affecting the value of the function. It's not affecting x, because we're not changing the value of x. Whatever we put in for x, it stays that value. But if this is negative, it's going to change the sign of the entire answer. If the answer is positive, it's going to make it negative. If the answer is negative, it's going to make it positive. So y is going to go from a positive to a negative. So it ends up, so if you look down here, y is going to go from a positive to a negative, or from a negative to a positive. So it just flips over this x-axis. And so it causes that reflection. Then for your translations, a horizontal translation occurs when you get your h. So whatever x is, whatever your h is, that is going to cause a horizontal translation, or right-left movement. And then that means that you're going to have a vertical asymptote. And we will talk about what an asymptote is. I'm just going to abbreviate it in a minute. Then your vertical movement is your up-down movement, and that's going to happen with your k. So k is going to move you along the y-axis, and that's going to be your up-down movement. And you will end up having a horizontal asymptote. So remember here, if something's being added or subtracted to x, that's going to cause this right-left movement. If it's a plus h, it's going to be to the left. If it's a minus h, it'll be to the right. And then if something's added or subtracted outside the function, if it's a positive k, it's going to be up, negative k will be down. So exactly as you see it, opposite of what you see it. And then this is everything combined with the a, the h, and the k. All right, so let's go ahead and look at a graph. So I can't make it too big or you won't see everything. All right, so we're going to graph the parent function right here, 1 over x. And 1 over x looks like the following. If you throw it in your calculator, or if you choose values, let's just go ahead and choose some values for x and come up with the y value. So I'm not quite sure what to choose for x, so let's just throw out -2, -1, 0, 1, and 2. So if I put in all of these are going to be, I'm going to have to slash my fraction. I don't normally slash fractions, but I'm short on room here. So I'm going to put a -2 in here, -1 here, 0, 1, and 2. Okay, so for this one, if I have 1 divided by -2, I get the value -1/2. This value here is going to equal -1. But this value here, 1 divided by 0, is not possible. Remember, you cannot have 0 in the denominator, so this is undefined. Your calculator will show error. And then 1 divided by 1 is 1, and then 1 divided by 2 is 1/2. So I'm going to plot these points on our graph above. So if I plot the point -2, -1/2, I'm going to be right here. And then -1, -1, right here. And then I can't plot an x value of 0, so 1, 1, and then 2, 1/2. I could choose some additional values to plot, but I'm not going to. All right, so I get what are called branches in my graph, because you see that this graph is discontinuous, meaning I cannot travel along here and end up over here. In order to go from here over to here, I have to make a jump. And as you can see, this graph is approaching the x-axis but never touching it over here and here. It's getting closer and closer, but it's never going to touch this x-axis. This x-axis is called an asymptote. And there's really this vertical line going right along the y-axis labeled x equals 0. That's known as our x-asymptote, vertical asymptote, x equals 0. And the reason for that is, so your vertical asymptote we get the vertical asymptote from the denominator. So use the denominator. So I'm going to take the denominator right here, x, and I'm going to set it equal to 0 and solve for x. Well, in this case, if I set it equal to 0 and solve for x, it's already solved. So x equals 0 is my vertical asymptote. X can never be a value of 0, so we have to remove it from the graph, so to speak. And so no matter what my y value is, my x is never going to end up being 0. X can be any other number, but it can't be 0. So for instance, look what happens. If I take 1 and divide it by 16, I get 1/16. So my x value is 16 and my y value will be 1/16. So if I plot all the way over here and keep going to the right, 16, and I only go up 1/16, I'm really, really close to this x-axis, but I'm still not touching it. Same thing can occur on this direction. If I put instead of a 16 here, what if I put a 1/16? So 1 over 1/16. So remember, when you have a fraction divided by a fraction, you take 1, and instead of the division bar, you multiply by the reciprocal. So I would get 16. So when x is 1/16, y is 16. So 1/16 would be really close to the y-axis, but not touching it, and then I would go all the way up to 16. So this becomes an asymptote, and as you can tell, this here is also an asymptote. It's the horizontal asymptote. Y is never going to have a value of 0 because there is nothing in the numerator that can create a 0 because there's a 1 there and there's no variable. Since there's no variable, the numerator is always going to be 1. And so there's no way, no possible way for that numerator to be 0 for the whole value of the fraction to be 0. So let me erase this. And we're going to put in our vertical asymptote, or I'm sorry, our horizontal asymptote. So I'm going to show you later, not today in this lesson, how to find the horizontal asymptote algebraically, but for right now you're just going to look for it. And in this case, because it goes through the y-axis at 0, it is y equals 0. And so we are going to put a dashed line here and label it y equals 0. So whenever we have up, down, right-left movements, these asymptotes here will move as well. They're always part of this parent function graph. So if I move to the right, so if I take this graph and move everything to the right, the horizontal asymptote can't move right because it's already in the right-left direction. But this vertical asymptote can be pushed to the right, it can be pushed to the left. This horizontal asymptote can only be pushed up or down. So a right-left movement or up-down movement is only going to affect one of those two asymptotes. So in this case, let's figure out what is our domain and what is our range. And we've already figured out these, so let's go ahead and fill those in. So we have x equals 0 and y equals 0. So then as we look at far left here, the leftmost value we go on the domain would be negative infinity. So this graph is going to continue infinitely, getting closer and closer to that x-axis, but never actually touch it, and it's just going to keep going forever. So our domain starts at negative infinity, but as I go from negative infinity and come in this direction, all of a sudden, boom, I hit this fence right here. This fence is a value that x can never be, and I have to jump over the fence. So anytime you have to jump over a fence, that's considered not part of the domain. So I come this way, I hit a fence, and I have to jump over it. That fence is 0. So my domain is going to go from negative infinity to 0, and we're using parentheses, not brackets, because at this point 0 right here, it's not part of the domain, so I don't want to include it, and if I include it, it would be with bracket. Then I'm going to jump the fence and I'm going to union the next part of the domain, and so once I jump the fence, I'm really close to 0, and then I go to positive infinity. So the other half is going to be from 0 to positive infinity. And so anytime we have an asymptote, it becomes part of our domain or range. The vertical asymptote affects my domain, not the range. However, the horizontal asymptote is going to affect my range, because here's the horizontal asymptote. As I go from negative infinity and travel along the y-axis to positive infinity, I reach another fence. Right here is the other fence that I have to hop over. So it's going to look just like the domain here. We're going to go from negative infinity. So we have a graph here at negative infinity. I reach this fence. There's no graph here. There's no possible way y could ever be 0. So I jump it, and I keep going in this direction, and this graph is going to be going and going and going forever. So the domain and range in this particular case are identical. So negative infinity to 0, jump the fence, 0 to, positive infinity. All right, so we have done everything that it's asked. We graphed the parent function, stated the domain, range, and vertical and horizontal asymptotes. Perfect. All right, so let's look at example 2. Make it straight. That would really bug me. Straighten, I forget more. Okay, the only thing that's different here from the parent function is this 4 right here. So this 4 is actually a. Because couldn't I factor the 4 out and say it's 4 times 1 over x? So 1 over x is our parent function, 4 becomes our a. So since a is greater than 1, don't we have a stretch? So when we have a stretch, that means that the branches that we had here and here, they're still going to be there because there's no reflection, but a stretch means we're going to pull them away from the origin. So you're going to see them pulling away from the origin. So I'm going to plot the parent function with this just so you can kind of see the difference. I'm going to plot this function first, and then I'm going to plot the parent function in there so you can see that this is actually stretched away from the origin. So since there's no right, left, or up, down movement, nothing's happening to x, nothing's happening outside of here, our vertical and horizontal axes have stayed the same. So let's state those. The vertical asymptote is going to be x equals 0. Our horizontal asymptote is going to be y equals 0. So we're going to plot those first. Okay, so this is our vertical asymptote. You should be using a straight edge. I don't get that pleasure. And then this is going to be our horizontal asymptote. All right, so then I'm going to plot our stretch. Now, since our asymptotes are the x and y axes, we are not going to have any x or y intercepts. So no x or y intercepts. All right, so let's go ahead and get an XY table here. So this time, when I put in a value of -2 in for x, I have 4 divided by -2 is -2. If I put in -1, I get 4 divided by -1 is -4. If I put in 0, that is undefined, it's not possible. If I put in +1, I get +4. If I put in +2, I get +2. All right, so let's plot those points. All right, so I'm going to plot -2, -2, and then -1, -4, and then 1, 4, and then 2, 2. All right, so that is the function y equals 4 over x. And you can see that it is further away from the origin than the parent function because I'm going to plot our ordered pairs from the parent function from before so that you can see the difference. So I'm going to plot the parent function in pink. So we had -2 and -1/2. We had -1, -1. So see how much closer these points are. And then if we did -1/2, we'd be at -2. So you'd have a graph that looks like this on this side. And then 2, and then let's do 1, 1, and let's do 2, 1/2. Oops, I missed that one, but that's close enough. So you can see this is the parent function. So it's much closer to the origin, and this is 4 over x. It has been stretched. We've taken this and stretched it this way. We've taken this one and stretched it this way. So it doesn't get stretched too much, so 4 doesn't create too much of a stretch, but it is a stretch. Now our domain and range is going to be identical to the parent function because our vertical and horizontal asymptotes have not changed. From -infinity, I hit a wall and I have to jump it at 0 and go to +infinity. So my domain is -infinity to 0, jump the fence, 0 to +infinity. Our range is going to go from -infinity to 0, jump the fence, to +infinity. So our range is identical. Jump the fence. All right, then we're going to describe the effect of A here and then compare it to the parent function. So they're not asking for the horizontal vertical asymptote or anything like that, just a description. And then we're going to graph it. I'm going to have you throw that into your calculator, and so you can see kind of how the graphs are different rather than take the time to put it in a table of value. So for this first one, we've got two things going on. We have a negative and we have A being 2. So there are two things that are occurring. With A being 2, so A is greater than 1, that causes a stretch. So with that stretch, it's going to stretch away from the origin. It's going to pull it from that origin. All right, then with the negative right here, So with that negative, it is going to reflect over the x-axis. So what does that look like? So if I had the original branch was here, so if it reflects over the x-axis, it's going to reflect here. So then this would be gone, and you would have, instead of in the first quadrant, it would reflect into the second quadrant. And then here, if I had my graph here, it would reflect across the x-axis to here. And so this one, oopsie, this one would be gone. And you would have a graph that's in the second and fourth quadrant. So we're going to graph that a little bit better, but that's what the reflection looks like. All right, so my parent graph I already know that my vertical asymptote is going through here. Yes, they always have to be on there. They are part of your graph. They help give you the shape to your branches. And then I know from my parent function, so I'm going to put my parent function y equals 1 over x in blue. So I know I have 1, 1 and negative 1, negative 1. Those are my main points. This one is going to reflect. So this one I'm going to put this one in pink. All right, so y equals negative 2 over x. So if I use the same values I've been using, so if I put negative 2 divided by negative 2, I'm going to get positive 1. If I put negative 1 in, negative 2 divided by negative 1 is positive 2. If I put 0 in, I can't because that's undefined. If I put positive 1 in, I get negative 2. And if I put positive 2 in, I get negative 1. So let's see where that puts us. So negative 2, positive 1 puts us here. And actually I'm going to put that in green so that I can see my points. So it's going to be in green. So not only do we have a stretch, so it should be further away from the origin, but it's also reflected into a different quadrant, which you're seeing happening right now. And then negative 1, positive 2 puts me right here. And then 1, negative 2 is here. And 2, negative 1 is here. And so now, oops, if I can pull that back. And then here, and then here. So as you can see, these are slightly closer to the origin than these points are. And it's been reflected into the second and fourth quadrants rather than where the branches normally are, which is in the first and third quadrant. All right, so I want you to try this one on your own. So pause the video and I want you to try to do that one all by yourself. Okay, so let me make this a whole lot bigger and straighten it out. Yeah, that's good enough. Okay, so for this one, if I pulled out a and it had the parent function, a would be 1 over 2. So let's see if I can get my colors back. So this would equal 1/2 times 1 over x would still give me 1 over 2x. So the reason why I did that was so you could see that this is the parent function and then a must be 1/2. So since a is less than 1 and greater than 0, we have a shrink. And so it's going to shrink closer to the origin. All right, so let's go ahead and graph this. Okay, so I still have my vertical asymptote here because there's been no up, down, right, left movement, and my horizontal asymptote at y equals 0. So that means that my domain and range is still going to be the same. That hasn't been affected yet. And then my parent function I'm going to put in blue, so y equals 1 over x. So I got 1, 1, and negative 1, negative 1. All right, so then in pink, I am going to plot x and y. So we're going to choose the same values. All right, so 1 over 2 times negative 2 is 1 over negative 4. So 1 over negative 4, negative 1/4. And then 2 times negative 1 is negative 2, so we get 1 over negative 2. 0 times 2 is 0, so this is still undefined at 0. 1 times 2 is 2, so we get positive 1/2, and 2 times 2 is 4, so we get 1/4. So plotting those points, negative 2, negative 1/4 is really close. Oh, I want to put that in green. Really close. And then negative 1/2 is closer there. And then 1 1/2 is right about there. And then 2 1/4 is really close. So this is going to end up being like this and like this. So you can see that that shrink is drawing the branches closer to that origin. All right, so looking at example 5, now we have some movement going on. So we have something happening inside the function and something happening outside the function. So this right here is inside the function, so it's causing a right-left movement. Because we are subtracting 2, it's the opposite of what you think it would be. So instead of left 2, it's really right 2. And the only asymptote that moves right-left would be the one that's the vertical asymptote, because this is the only one I can move right-left. If you try to move this line right here, right-left, it's going in the right-left direction. It can't move right-left because it's already pointing in the right-left direction. So I can physically move this and create another vertical line here or another vertical line over here. So what that means is our vertical asymptote is going to move to the right 2. So if our vertical asymptote used to be at x equals 0, now we're going to add 2 to that 0, and it's going to become x equals 2. Our horizontal asymptote is going to be affected by what's happening outside the function right here. So this is moving in the same direction as you think it would, so it's going to move up 3. So the only asymptote that can move up is this horizontal one can be moved up. So your horizontal asymptote is going to be y equals, and we're going to add 3 to that 0. So those are the first things I'm going to graph. So I'm gonna graph both of those asymptotes in red. So x equals 2, and both of these are going to affect the domain and range. And then so this is y equals 3. And so since I don't have a reflection, I know my branches are going to be here and here. So we are going to get an x and y intercept as well. So that's something that you need to learn to figure out. So I'm going to put that, we're going to start talking about that. So let me go ahead and show you how to find that here. So x-intercept remember that y is equal to 0. That's a y. So I'm going to let y equals 0 in the equation. So y equals 1 over x minus 2 plus 3. So to find the y-intercept, I'm going to subtract 3. So I get negative 3 equals 1 over x minus 2. The easiest way to get x out of that denominator is to create a proportion and cross multiply. So if I cross multiply, I'm going to get negative 3 times x minus 2 is equal to 1. Distribute your negative 3, so I get negative 3x plus 6 equals 1. Subtract your 6, negative 3x is equal to negative 5. I know I'm running into those words. And then divide by negative 3, you get x is equal to 5/3. So my intercept is going to be 5/3, comma, 0. So I'm going to plot that point. So 5/3 is what, 1 2/3? Right here, give or take. Then my y-intercept, let's change colors. How about a bright green? So then my y-intercept means that x is going to be 0. This one's actually easier to find. So y equals 1 over, and instead of x, I'm going to let x be 0, minus 2 plus 3. So then just do your math. Y is equal to 0 minus 2 is negative 2 plus 3. Negative 1/2 plus 3. Y is equal to 2 1/2. So your ordered pair would be 0, 2 1/2. So we're going to plot that. Right, change my color. 2 1/2 would be right here. So that gives me enough information that I can actually go ahead and graph my branch because I have enough information for the shape of it. But over here, I probably want to choose a value for x in order to get some starting point over here. And so I like to stay pretty close to my asymptote. So since this is 2, I'm going to choose a value for 3 for x. So if I find f of 3, whoops, I wanted blue, f of 3, and I'm just choosing 3 just because it's close to the asymptote. So I get equals 3 minus 2 is 1. 1 divided by 1 is 1 plus 3. So f of 3 is equal to 4. So when x is 3, y is 4. So right here. So that gives me an idea of how close to get to that intersection. And so there we are. There's our graph. So let's make sure we answered all questions. Oh, state the domain and range. So our domain and range are going to change a little bit. So as I go from negative infinity on the x-axis, I travel, I hit no blockings, and I've got a graph all the way over here. So I have a graph from negative infinity up until I hit this wall, which I have to jump. This wall is at the number 2. After I jump it at 2, then I continue on into positive infinity because my graph is still here at positive infinity. So 2 is our jumping point. So for my domain, I go from negative infinity till 2 until I reach that fence and I have to jump it. And then I go from 2 to positive infinity. Then for the range, I still have a graph all the way down here at negative infinity. Keep going, 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 still have a graph, oop, until I hit this wall, this fence, I have to jump it. That fence is at 3, and then I keep going to positive infinity. So my range is going to be negative infinity to 3, union 3 to positive infinity. So note that your vertical asymptote of 2 is affecting your domain. Your horizontal asymptote of 3 is affecting your range. So now we are going to write an equation for the translation of y equals 3 over x. It's pretty close to our parent function, except for instead of 1, we have a 3 here. And they're going to give you some asymptotes. So I'm going to do the first one with you, and then you get to do this one on your own. So let's make this bigger. All right. So I have the parent function of y equals 3 over x. This value right here is your vertical asymptote. Vertical asymptote affects your right-left movement. So it affects your right-left movement. Your right-left movement is over here inside the function. So whatever this is, we're going to add or subtract it to the x. This is affecting, this is your horizontal asymptote, and it affects your up-down movement. So since it affects your up-down movement, it's going to affect the outside of the function. So in this case, it's a positive 2, and we want it to be exactly as we see it, so we have a plus 2. So our final value is going to be y equals 3 over x, because x plus 0 is still x, plus 2. All right, so I want you to pause the video and do part B. All right, so if we start off with y equals 3 over x, remember this is our vertical asymptote. It affects our x value, or inside the function. So since it's a minus 2, we want to do the opposite inside the function and add 2. This affects the outside, so we're going to add exactly what we see, a plus 1. And this is your answer. And then our final problem is going to be a lacrosse problem. Okay. There we go. Okay. I have no idea why they spelled lacrosse this way. In fact, it's bothering me so much, I think I'm going to respell it the correct way. So there shouldn't be a space in there, and it should look like this. There we go. Okay. So the lacrosse team is renting a 52 passenger bus for the day trip. So we are restricted to 52 total passengers. The cost of the bus is $650. So that's what it's going to cost us, no more, no less. 4 of the passengers will be chaperones. So at most we can have 48 students and 4 chaperones. If the students who attend share the cost equally, what function models the cost per student, so C is going to be our Y, with respect to the number of students N who attend. So N is going to be our X because the number of students drive the cost. The cost does not drive the number of students. So we are going to let N equal number of students. And we're going to let C equal cost per student. All right, so a couple of things that are important. If you were to figure this out, I mean, the easiest way to write your equation would be to figure out if I knew all the information, which I kind of actually do. The only thing I don't know is how many students there's actually going, but I do know it's going to cost $650 for the bus. The chaperones are not going to be paying any cost for the bus because they're volunteering their time, they're chaperones. So if we take, and I know that I can only have at most 48 students, but what if I only have 10 students? So I don't know how many students I'm going to have, but wouldn't I take that total cost and divide it by the number of students? So cost is going to equal the $650 divided by however many students are on that bus. The extra information, or the information that's supposed to like throw you a little bit, is the 52 passengers. That has no bearing on the equation that we write. the 4 passengers also has no bearing on the equation that we're going to write. And then this final question down here where it says how many students must ride the bus to make the cost per student no more than $20, that's going to happen after we figured this out. So this is our equation to solve. The question that they want to know, so that's one of the questions, what is the domain of the function? I don't have anything added to this value underneath here or outside here. So that means that my domain normally would be negative infinity to 0, union 0 to positive infinity, and that would be our range. However, we know that we can't have any negative students, right? Because n is our domain. And I can only go from, and I'm not going to have 0 students, so I can only go from 1 to 48 students. So our domain, my domain is going to be from 0, because we're not going to include 0, that's why it's a parentheses, from 0 to 48. So instead of positive infinity, we have to stop at 48. Now our range could be, I mean, if I had 1 student, it would cost that student $650. I really hope there's not 1 student on the lacrosse team. But 1 student would cost $650 all the way up to 48 students. So let me divide that out. All right, so I'm thinking, so sorry. So I'm going to take, so my highest cost per student would be $650. My lowest cost per student would be divided by 48. That would be $13.54. So my lowest range actually would include, so I'm going to put brackets. So it'd be $13.54 all the way to $650, and it would actually include that because this is a real life example. So that's the domain. Oh, they didn't ask for the range, so I just gave that. That's extra information. So how many students must ride the bus to make the cost per student no more than $20? So for that, we're going to replace cost with $20 divided by n. So to get n out of that fraction, create a proportion and cross multiply. So if I cross multiply, I have 20n is equal to 650 divided by 20, and I get 32.5. Well, I can't have half a student. If I only have 32 students, 650 divided by 32 is $20.31. So I can't have 32 students, therefore I must have 33. So therefore, there must be at least 33 students to keep the cost. That's an E. Well, no matter how much I try, it's no longer looking like an E. To keep the cost to $20 per student. And there we go. Have a great day.